Since this lecture focuses on Euclidean domains, the next thing that we'll do is give a definition of a Euclidean domain. Let's say that R is an integral domain. A function n that takes an element of R to a non-negative integer such that n takes 0 to 0, so the additive identity of R has to get sent to 0, is a norm on R. So for something to be a norm, it's just a function from R to the non-negative integers that sends the additive identity of R to 0, no other requirements at all. If the norm of A is positive for any A in the ring except 0, then n is called a positive norm. Okay? An integral domain R is a Euclidean domain or possesses a division algorithm. So first important thing, Euclidean domain and possesses a division algorithm are used interchangeably in Dummett and Foote. So what is a Euclidean domain? It's something that possesses a division algorithm. If there is a norm n on R such that for any two elements A and B in R, where B is not 0, there exist elements Q and R in the ring where A equals Q times B plus R, with R is either equal to 0 or the norm of R is less than the norm of B. So what does this look like? It looks just like the division algorithm in Z and in F bracket X. So what is this Q? You should think of Q as being like this quotient of A by B, and R is the remainder when you divide A by B, except we're in a ring where things don't necessarily have inverses, so we're not exactly dividing, but that's what's going on in this division algorithm. So Q is this quotient, R is this remainder. Whenever you have A and B in the ring, B not 0, A equals Q times B plus R, where R is 0, or the norm of R, we don't know what it is, but it's less than the norm of B. Okay, so this is the first big definition here. We're giving a sort of more general idea of what it means for a ring to have a division algorithm. All right, so there's something I want to address before getting further into this, which is why is this called the Euclidean domain? And to try to answer that, I'll first remind you, what does the Euclidean algorithm do in Z? Well, one thing it does is it tells you how to compute the GCD of two integers. So what is the GCD of 2210 and 1131? What's the idea? You apply the division algorithm, and then you apply it again, and then you apply it again, and then you apply it again, and at some point, you have one number dividing another. So what happens here? 2210 is 1 times 1131 plus 1079. So first, we applied the division algorithm with A equals 2210 and B equals 1131. Now we're going to apply it again, but we're going to apply it with A equals what used to be called B, 1131, and B is going to be what used to be the remainder, 1079. 1131 is 1 times 1079 plus 52. Okay, and now we're going to apply the division algorithm again, where A is what used to be called B, and B is what used to be the remainder. 1079 is 20 times 52 plus 39. We're going to apply it again with 52 and 39. 52 is 1 times 39 plus 13. Now we're going to apply it again with 39 and 13. 39 is 3 times 13 plus 0. Okay, so now we can't apply it again because what would we be applying it to? We would be applying it with A equals 13 and B equals 0. But you can't divide by 0 like in this idea. Okay, this isn't in Z, this is in a general integral domain here, but it doesn't make sense to apply a division algorithm where B equals 0. So this last non-zero remainder we get, that's an indication that we hit remainder 0, and that's an indication that we stop. And this last non-zero remainder that we got, 13 here, that is the GCD of the two numbers we started with, 2210 and 1131. So let me point out that if you just go down this stack of equations, it's easy to see why 13 is a divisor of both 2210 and 1131, right? Like 13 just divides everything in sight because 39 is divisible by 13, 13 is divisible by 13, so 52 is as well. 39 is, 52 is, 1079 is as well. 1079 is, 52 is. So everything in sight is divisible by 13. And with a little bit of thought, you can see why, in fact, this is the greatest common divisor. Why there can't be another divisor of both 2210 and 1131 that is larger than 13, or there's no number of the form like 13 times d that divides both of these things, where d is a positive, or sorry, where d is greater than or equal to 2. Okay, so just to clear up what's coming, I'll now talk a little bit about Euclidean domains in general. In this lecture, we'll see that every Euclidean domain is a PID following the kind of arguments that we saw in the special cases of Z and F bracket X. And in the next lecture, we'll talk much more about Euclidean domains and GCDs.